All right, good morning, everybody. My name is Halvar, and the title of my talk is Why Johnny Can't Tell If He's Compromised. This is in relation to a talk that, or actually an article / book from the 50s about Johnny being unable to read and what can be done about it. Now, let me start this talk with quoting Robert Morris Sr., great scientist, probably one of the most important people in computer security over the last 40 years. And he coined the 3 fundamental rules of IT security, or of computer security. And this was done at some point, I suspect, in the 80s. The 3 rules are: do not own a computer, do not power it on, and if you have to own and power on a computer, do not use the computer. Now, if we look at what happened in the last, well, 1.5 years or so, with the Snowden revelations and everything else, it does seem that we haven't made much progress in the sense that, well, we still have no idea how to keep computers secure. And the fact that we can't keep computers secure is coupled with a fundamental addictiveness of hacking, meaning everybody trusts everybody else in some way, shape, or form. Transitive trust is everywhere. We have this huge graph of trust relationships on the internet or in our infrastructure. And the interesting thing is that you can start hacking pretty much anywhere in this huge graph, and then just follow trust relationships around the graph. So you hack one organization, then you use the trust that other people have placed in that organization to hack the next organization. And as you continue hacking, it gets easier and easier to compromise more. So hacking is one of those drugs that actually get better as you take more of them. And this has turned hacking into something that is really, really addictive. And, well, as you hack, it gets cheaper and better. So in the limit, the only thing that keeps you, or that limits the growth of your compromise, is pretty much the size of the network you're hacking and your administrative infrastructure to administer all those compromised machines, because, well, they're now yours and you have to manage them somehow. So if we look at the situation of all our infrastructure in our networks now, we have a sort of race to the bottom where all the big nations wish to have cyber dominance. So everybody essentially wants to be able to compromise everything else at will. This is a clear policy goal of most major powers. They wish to have dominance in this new domain. So you've got a bunch of people that are paid and that spend big bucks on, well, compromising everything. And at the same time, we're not very good at doing defense. Literally, there's very few organizations that play at proper defense at all. And even those are not all that great. I mean, they're better than the rest of them, but yeah. So in the limit, what we're seeing at the moment is the internet gets more and more important. We get this awesome thing called Internet of Things. At the same time, nobody knows how to play defense, and many major countries want to play offense at the same time. So we get into this bizarre situation where we have an internet of compromised things, like the network is everywhere all the time. At the same time, we have 2 or 3 different parties that are compromising everything at all times. So, well, given an arbitrary computing device, it's quite likely that multiple parties you don't like have access to it at the same time. Let's talk a little bit about what compromise means, because a compromised machine is a bit of a fuzzy concept. Clearly, if you install your code on a machine and it runs with high privileges, you've compromised that machine. Fair enough. At the same time, you don't need to install code on the machine to have compromised the machine. If you get the root password from somewhere, or any form of authentication credentials that allow you to log in and then do whatever you want with the machine, you've still compromised the machine. So compromise of machines is really about control of machines. And this is where computers are fundamentally, or computing devices that are networked, network computing devices are fundamentally different from everything else we know in the physical world. Now, in the legal world, you've got the distinction between ownership and possession. Meaning I own my car, but I've lent it to a friend, so I'm not currently in possession of my car. And these are 2 different concepts, and oftentimes it's assumed that whoever has possession also controls the device at that point, or the entity at that point. So if somebody else, like I may own the car, but if somebody else has the car currently, I may not be able to access it. The interesting thing about network computing devices is you've got a 3rd dimension. You have the control dimension. You may own, meaning have legal title to a network device. You may possess it. It may be in your data center. It may be in your living room. You may have 0 control over it. So if you think about hacking and being hacked. Being hacked is literally about the loss of control over your own computing infrastructure. And it's interesting in the sense that I don't think we historically have much of an analogy for this. Because, well, historically, if you were the one that actually, was in possession of something, and, well, you had it there and you had control over it at that moment. So this brings me to the next point. If you try to figure out, well, you just try to establish, I have a computing device, who is in control of this? And then things get really dark really quickly. And this talk, the content of this talk will essentially be an exploration of all the ways we can't tell who's in control of our computing devices, and then talk a little bit about what we could do to fix parts of it. So let's do a little bit of a thought exercise. Let's assume that we've got a Windows machine. Somebody hands you a Windows machine, and you start to try to establish who is actually controlling this machine. Let's think about this for a moment. Clearly, all the highly privileged code running on that machine is in control. Fair enough. Any user code that is running is also in control somewhat. Might not have the same level of control that privileged code has, but it's partially in control. Pretty much anything that runs in that machine has some notion of control over the machine. So this means that I have already made the decision up front to delegate control over my machine to whoever I've trusted with the installation of software on my machine. So I've decided I'm going to install an operating system. So I trust Microsoft, or I delegate control over my machine to Microsoft, or to the Debian guys or whatever. And that's quite OK, because I'm aware of doing this delegation. I've made a conscious trust decision. OK, I'm going to trust these guys to at least not put backdoors in maliciously or not screw me over maliciously, because I've got some sort of contractual relationship with them and some level of trust. So if I have a machine, I need to establish whether all the code that is in that machine and running in that machine is actually code that I have decided to trust. I need to be able to verify only stuff that I delegated control to actively, meaning with my own decision, is, well, running in that machine. So there's roughly 7 things that you need to do to establish this. First of all, you need to verify signatures on all user space binaries, which means, well, for everything that runs in user space, you should know where it's coming from, and you should know that you trust the people that have provided you with the software. Then likewise, for everything that's running in the kernel, you should know where it's from. You should know I have trusted these people with it. OK. Likewise with the BIOS. So everything that runs in the BIOS, EFI, whatnot, you should know where it's coming from. You should be able to verify where it's coming from. And you should know, hey, I've made a conscious decision to trust these guys. Same goes for firmware devices, meaning GPUs, hard disk controllers, and so forth. Stuff that's been put onto your main board without you knowing, like Intel's management engine. And now comes an important thing on the bottom right here, which is after you've verified that all these things are signed and that you trust the people that have signed this, the next thing you need to do is you need to verify whether the signers actually know that they've signed this. Let me repeat this. We have to verify whether the signer knows that they've signed this. The trouble with everything that we've built in terms of PKI is we have always assumed that the PKI is going to be impenetrable, meaning the certificate authorities don't get hacked, and the people signing our stuff won't get hacked, and they won't lose the keys. Now, reality isn't like this. It is very, very clear that people have been stealing code signing keys all the time, and they've been hacking CAs all the time and stealing their keys. So once a key is compromised, there's no way for us to figure out whether it's been signed by the original party or by some third party who stole the key, unless we sync back with the original party and ask them, hey, have you signed this? And then the last thing we need to do is we may have a situation where we're running a whole bunch of interpreted code on the machine, Java code, Python code, whatnot, and we need to verify where this code is from and what it's doing. So there's 7 things we need to do. And let's try to do these on the Windows machine under consideration. Let's try to establish whether we control this. Let's look at user space code. So the first problem you'll run into is vendors don't sign the executables. Microsoft signs all of their executables. That's a good start. So everything that is provided by Microsoft on your machine is most likely going to be signed and will verify. The trouble is other vendors don't. I checked Adobe yesterday, and Adobe signs all their main executables, and they don't sign any of the DLLs they're loading. So this is great. You now load untrusted libraries. You're screwed again. So let's assume for a moment that they would sign their DLLs. The next thing they do is there's executable modules that are not explicitly marked as a DLL, plugins to the document viewer, whatnot, that are also not signed. So first problem, nobody signs their code. If they do it wrong. And if they do it incompletely. The next problem is your Microsoft Windows box trusts SSL-wise more than 100 root CAs, which contains a whole bunch of organizations you've never heard of and would never think of trusting. And it's really quite unclear which proportion of these have code signing certificates. There used to be a website, like Microsoft used to have the list on the website. I checked yesterday. There's just not a clean list of who is actually trusted for code signing. So we fail completely at validating user space code. Then let's move on and try to validate kernel space code. Now, the number of CAs that are allowed to sign drivers for Windows is actually relatively low. It's like less than a dozen. So there are many fewer people signing drivers. You would think that this is actually a good thing, and this will prevent attackers from loading malicious code into kernel space, but it's completely irrelevant. All signing of drivers is irrelevant because the attacker can just downgrade to a vulnerable version of a driver and then use that to bootstrap code into kernel space. If you look at what Ouroboros, like this Snake rootkit did, they delivered a pre-signed version of a virtual box driver with a known vulnerability and used that to, well, leverage ring 3 execution into ring 0 execution because they could load the signed vulnerable driver. So this is a huge problem with all code signing. People can downgrade to vulnerable versions easily, and if you don't start blacklisting older versions of everything, then, well, you're still screwed. So we've got no way of validating kernel space code either. So we fail completely there as well. Let's talk a little bit about BIOS. Let's have a look at the BIOS code. So what does a BIOS consist of? It's usually, well, the core of it is written by somebody like Phoenix or AMI BIOS or whatever. And they sell a sort of SDK to original equipment manufacturers, HP, Dell, and so forth. And then these companies do a whole bunch of magic to this SDK that they've gotten, and then they build some form of BIOS blob from it. And this BIOS blob is then put on the hardware, and yeah, every vendor implements their own signing and validation. Nobody documents how it's done. Aside from the fact that nobody documents how they're validating BIOS images, there's also areas of memory, of flash memory, that are inaccessible to the main CPU. So literally, there's no way for a third party to validate signatures on any BIOS ever. It's just can't do it. So even if there was a proper documentation on how to verify the BIOS blobs, it doesn't help you much to verify them on disk because, well, you need to verify whatever is running in flash. And there's no way you can't read it, and that's bad. So BIOS code, we can't do it either. Let's talk about HDD or device firmwares. So let's start with talking about HDD controllers. We've seen in the Snowden slides that there's some sort of backdoor that the NSA has built that is used on Dell PowerEdge servers with RAID controllers, whatnot. And that regains periodic execution at times. So clearly we know people can install code on hard disk controllers. And you don't have to be the NSA to do it. There's a link on these slides here of some guy on the internet that has literally installed Linux on his hard disk, and not meaning installing Linux on his hard disk, but Linux on the hard disk controller. Meaning there's 3 ARM cores in his hard disk, and then he identified one of them and managed to actually flush a Linux onto the boot ROM of that embedded controller, and then boot Linux on the actual chip in the hard disk. And this is like hobbyist work, right? So we know that hard disk controllers and the chips inside can be backdoored, except we have no way of doing so. We don't know how to read out the memory in the hard disk controller. The vendors are not forthcoming. Nobody tells you how it works. So yeah, we literally have to live with the fact that we're putting something in there that we do I/O on all the time, and we have to live with the fact that this thing may be untrustworthy and may be trying to manipulate binaries as they're being read. So hard disk controllers, we've got no chance to actually verify anything. GPU firmware. So we now have GPUs in most desktop machines, and these GPUs have their own computing environment, and they load their own firmware. Again, all of this is undocumented, but you will find people online that are modifying these things and overclocking their GPUs and so forth. So we all know this is modifiable. It's just that by the very architecture of it, there's no way to verify it, there's no way to read it, there's no documented form of getting any assurance that what is running is what you intend there to be. So yeah, when it comes to, I mean, things look bad on user space code, they look bad on kernel space code, and then they look really bad on BIOS, and once we reach devices, we're literally stranded. There's not much we can do. So failure number 4. Failure number 5, Intel Management Engine. Now this is a real beauty, because nobody really knows why on earth anybody would think this is a good idea. Intel has decided to put an extra core on your main board, a sort of co-processor for your main CPU. It's an ARC core that gets its own MAC address and can talk to the network, and can talk to your RAM directly via PCI shared memory bridge. And it can execute signed Java applets and do all sorts of management stuff, contains a web server, whatever you want. And the awesome thing is most of the memory that the management engine uses is not readable, like physically not readable from the main CPU. So the value proposition there is I'm going to put a hardware thing into your machine that you're buying, and this hardware thing is unserviceable by you, is intransparent by you, or to you, can do whatever it wants, can load third-party code, provided the vendor has signed it, and you've got no way of knowing what the hell is going on. This is almost the perfect example of complete loss of control over your own compute infrastructure. So we can't verify anything in there, and the really, really bizarre thing is all the previous points were failure by incompetence, meaning in theory, if everybody was willing and was trying to help, we could validate signatures on user space binaries and on kernel binaries, yada, yada, yada. But on Intel Management Engine, this is actually, like the opacity is a feature, not a mistake. So, yeah. Now, next step, dealing with stolen keys. Well, this is actually a relatively deep problem, because when we ended up designing all the public key infrastructure for everything, for some reason, we always assumed we can keep keys safe. If you look at SSL, for example, it just wasn't in our threat model that we would have to invalidate a large quantity of certificates. That's why OCSP doesn't work properly. So everything we've built fails to, well, deal with the fact that keys do get stolen all the time, and they get stolen in bulk. What happened with SSL certificate authorities was that people eventually realized there's no way I can trust a certificate authority, like a random certificate authority, if they can issue a root certificate for Google.com, Microsoft.com, and so forth. So, well, you talk to some of the lawful intercept guys, and they will always say, well, intercepting SSL isn't a problem. You can always find a friendly CA. And this realization that the CAs have it in their business model that they're cooperating with the exact people that you're trying to prevent or to protect from, this realization led to something called certificate transparency, which is a project run by Ben Laurie and a few other SSL guys. And what they're trying to achieve there is they try to achieve a public ledger where every certificate authority has to publicly publish everything they've ever signed. And the idea behind this is that the certificate authority can no longer, under the hand, give somebody a root certificate for Microsoft.com, because everything that they have signed has to be made public. And we need something like this for code. We need a public ledger that contains every piece of code that somebody who signs code has signed. Microsoft needs to publish a list of all the executables they've ever signed. Google has to publish a list. Everybody who signs code and establishes trust based on this has to publish this list. Well, because otherwise, there's just no way anybody can ever detect that the signing keys have been stolen. And we know signing keys have been stolen because Bit9 keys were stolen at one point. That was quite public. And we also know that whoever went into RSA was trying to steal signing keys there. So without the public ledger, we're really in no situation to, well, deal with signatures in a sane way. So it's not quite a Bitcoin ledger, but it's something quite similar to it. So, but while we need this, it's not there. Like, none of the vendors publish lists of things they've signed or even have lists of things they've signed. So if you find an executable on your machine, and it looks like an Adobe binary and it smells like an Adobe binary, you don't know whether Adobe has actually produced this binary or whether Adobe was in control of their keys when this binary got signed. So, yeah, another failure. Last thing, scripts. Yeah, we are typically running lots of different interpreters on our host nowadays, all with privileges and very, very trusting. Look at all the JavaScript-based extensions to your browser, all the Java-based background tasks and so forth, all the Python stuff you run in the background. The trouble with all of these things is you've got no way of tying what is running in your machine back to the script. The JavaScript will get jittered, and then there'll be some executable blob in memory, and this executable code is unverifiable to you. You have no way of tying that code back to the script. So that code may do anything at all. You may backdoor somebody with a binary blob in the region of code that he jits stuff in, and he'll just have no way of figuring this out, unless he starts disassembling the JIT code and then understands that somehow the JIT code is not what he thinks it should be doing. But it's not like he can tie this back to any script anyhow. So this is the other big weakness of all this code signing. As long as you've got interpreters that are incapable of tying the code that they're actually executing back to the code they used to generate this, you're still screwed. So we need to build interpreters that can do this. So we're through with our list of baseline checks. And it's a bit of a depressing picture, because literally, if given a machine nowadays, I've got no way of determining whether this machine is owned or not. The only safe assumption is to toss it away as soon as I suspect it's owned. And that's clearly not a very economical nor environmentally friendly alternative. So, yeah, what needs to change? What do we need to engineer differently organizationally or at the actual engineering level to make sure that we can identify whether things are owned, and secondly, have a fighting chance of uninfecting a machine? So, short warning, all my proposals are wildly impractical. I'm a mathematician at heart, which means that I'll propose things and then it'll take a couple of years to actually make them useful. What I find interesting about this entire thing that I'm proposing now is that I am of the opinion that technically, most of this isn't terribly hard. It's not like unsolved research problems like proving absence of buffer overflows, period. It's more of the obstacles are more organizational and managerial in nature, meaning it's going to be hard to implement these things, not because they're technically hard, but because different companies have different incentive structures, and we all fail at setting incentives that actually enhance security. So the first step that everybody needs to start doing is we need to start checking who we're trusting. If you look at the way that IT departments work these days, they do not ask themselves the question, who are we delegating authority to? At the same time, there's a strong misconception that, well, you won't be a target, so you don't have to secure yourselves. This is a misconception because other people trust you, and you're going to be the weak link in the chain. You're going to be the incompetent but well-intentioned person that gets owned, and through your incompetence, others get owned. So the trouble really is that nobody looks at vendors these days and is like, that vendor has a history of getting owned by attacker groups. We can't trust his software now. And that's something that will need to happen. An interesting thing is that if you talk to lawyers, they have solved a few of these problems, solved for some values of solved, of course. But But this entire idea of giving control over your compute infrastructure to other people, it's essentially, in legal speak, a delegable power of attorney over your compute infrastructure. And it's really fascinating if you talk to any lawyer about, hey, why doesn't your company give a delegable power of attorney over all its assets to company Y? The lawyer will first look at you in horror and then start laughing and walk away. But we do this all the time for computation. We are trusting random CAs, and a CA is allowed on our behalf to, well, allow others to run code on our network. That's literally what the job of a CA is. We allow auto updates of software from companies that we don't trust to keep their own computers secure, and much, much more. So we really need to start thinking about who are we trusting in this machine. So yeah, talk to your legal department or to any lawyer about this, and they'll laugh at the entire idea of providing a delegable power of attorney to a third party. It just doesn't happen. You don't do that stuff. I mean, would you give somebody you meet on the street and you buy, I don't know, bread from, a power of attorney over your bank accounts? I suspect not. The second thing is we need to undo the proliferation of certificate authorities. A code signing CA is an immensely powerful position, like ridiculously powerful. So there's way too many of them. There's no reason why there should be hundreds of them. There should be a very, very small number, and you should know your CA, and you should only trust your CA if you know your CA. And right as of now, I think almost no organization knows anything about their CA except that they're a CA. So we're literally trusting random strangers with everything. Bad idea. The next thing that we need to start investigating is whether the certificate authority model is even the right model for code signing. Because a certificate authority has the implicit power to sign random bits of code, but they don't have the resources or the inclination to actually look at this code in any way. On the contrary, they're paid by the people that are writing the code to sign the code. So the entire idea of allowing a CA to decide what code you are allowed to run and not might be fundamentally broken. So when it comes to code signing, the trust relationship really shouldn't be you to the CA. The trust relationship should be you to the vendor, or to the provider, or to Debian, or whoever. The guy that writes the software is the guy you trust, not the third-party authority that gets paid to issue trust certificates. The CA-based trust is really only acceptable in the very limited environment of a sandbox inside your browser for JavaScript and HTML. Next step, we need update transparency. At the moment, no matter what software you install, almost all of them have their own hand-rolled update mechanism. Aside from the fact that many of these are broken and will just be cryptographically weak, not properly verify whether the code is signed, and so forth, there's no transparency for you as the guy trying to keep the machine safe in terms of what actually gets installed and when it gets installed. So we need standardized protocols for installing updates, and all the applications need to start adhering to these protocols or not update, period. Signing transparency. I talked about this before. We need the public ledger where everybody that signs code publicly avows, yes, I have signed this binary, this is my code, and ideally with a sort of SVN tag or Git hash to tell, this is my code and was produced from this point in time out of my code versioning control system, so that later on they actually have some sort of trace where a binary might have come from, and they can double check whether the binary they're looking at is the binary they produced. And I'm harping on about this in multiple slides while repeating myself, primarily because I think there's no other way to engineer detection of key compromise into our infrastructure unless we do this. And we have to deal with the fact that keys have been stolen. Don't think that anybody would go into Adobe or Microsoft or any other large organization and not try to get the update signing keys. And we're also underestimating the importance of these keys in terms of, we all talk about O-days and exploits and so forth. We've got an adversary that sits on every wire, on every backend, like on every trunk connection anywhere. So he's always a man in the middle. He'd be stupid if he didn't try to just update us instead of exploiting us. And if he's got the keys, he doesn't need O-days. Step 5, we need to reduce firmware opacity. There's just no excuse for a piece of firmware to not be readable by the main CPU. And we need to engineer things in a way that's physically impossible for the firmware to not be, like, to tamper with the reading process. So something where you ask the firmware, hey, could you please send me a copy of yourself, is not good enough. You need something where you've got a direct memory access from the main CPU to the memory of the firmware, and you need to be able to read that stuff and validate it. And we, as purchasers of hardware, everybody that buys a piece of hardware needs to understand that they've got a right to insist on this. You're buying a piece of hardware, you should be entitled to control of your hardware, and you should be able to validate that you control this hardware, and therefore, stuff has to be engineered so it allows you to validate it. And this stuff isn't hard either. Like, DMA isn't rocket science. We've done this before. Yeah. Then management engine, there's just no excuse for management engine in its current form. Like, literally no excuse. There should not be a CPU on your mainboard whose memory you can't read, who has control over your CPU. I mean, I can't even, yeah, I have a lack of words to describe my incredulousness at the stupidity of that idea. So purchasers of hardware have the right and need to realize that they have the right to demand, I want to be able to read all the memory that ME has. I do not want any code to execute inside ME that I can't look at. This is folly and insanity. And this is going to be rough because Intel is pushing really hard to get this into every machine everywhere. And I think what they're taking a divide and conquer approach, right? No individual purchaser of Intel hardware has enough marketing power to really hurt them. So they can just split them and be like, well, if you don't want it, then go find your chips elsewhere. Step 7, we need signing interpreters if we're running privileged code in an interpreter. Meaning, if you're going to run a script and it's supposed to have any privileges, we need to engineer the interpreters in a way that there's a way to tie the executing code back to the original script that it was derived from. It's also not terribly hard. It is a bit of an interesting engineering problem. It would make for an awesome master's thesis in computer science if anybody knows a bright student. And there's a bit of a deeper thing that we need to think about as security industry. We need to engineer systems so they're easily verified and their integrity is verified by the owner. This entire idea of making things opaque and then centralizing trust in a foreign entity, in a CA, in a third-party vendor, is just a failed experiment. Meaning, there's no way that third party isn't going to get compromised. Let's look at Intel Management Engine for a second again. There's just no way in hell that Intel will not have to turn over the signing keys for Management Engine if they receive a national security letter stating so. So Intel is helpless against this adversary. So we can't trust Intel to keep that thing secure, because we know they have to turn over the keys. So the only way we can trust anything is if we can verify it ourselves. So we need to have a paradigm shift where we start demanding systems where we can verify the integrity and we don't have to trust the third party. Yeah, and this is actually a bit our own fault. If we look at stuff like TPMs and smart cards and so forth, historically we've prioritized side channel resistance and resistance against physical attacks over transparency. So tamper-proofing was much more important than transparency of chips. But tamper-proofing is a bit of a failed experiment in the sense that it seems that the attacker always, like the well-resourced attacker, will always bypass the tamper-proofing somehow. And the only person that is really incapable of knowing what's going on thereafter is us, because the attacker has bypassed the tamper-proofing, sits in something we can't look into, and we can't get him out or even detect him. So we need to reprioritize the transparency and verifiability of things over tamper-proofing. And yes, this will probably come at the cost of having less side channel resistance in your hardware, which need not be a problem, provided you can stay in possession, in legal, in physical possession of your hardware. But as far as I'm concerned, I'm much more worried about the remote attacks on everything I own than I am concerned about the physical attacks where somebody has to go and actually touch my device, mainly for cost, because remote attacks scale arbitrarily and cost nothing, so it's easy to build a full surveillance society on top of it. If you actually need to have somebody walk up to a device and do something to it, that's expensive and can't be done at scale. So we need to reprioritize verifiability over tamper-proofing. Now, will any of this give us security? And no. It won't yield us 100% security. But at least it will give us a fighting chance to detect persistence and to fight back against persistence. Because as things stand today, it's really, really hard to do anything. It's almost impossible on Windows. It's relatively, or it's pretty hard on most Linux machines. Yeah, so if we implement all this, at least we have a fighting chance of looking at a machine and deciding, at this moment, is this compromised? And the hope is really that once you get to the point where you've implemented all this, the only way that an attacker can have persistence is by recurrent exploitation, meaning he finds an application that runs on your machine regularly, that trusts a long registry key, and then every time that application runs, he overflows a buffer inside the application from the registry key and gains recurrent control over exploitation. But that's really hard. And it's really hard and application-specific. And I'm kind of hoping that if we implement all this, we can move the attacker, or we can make persistence expensive enough that the attacker has to exploit and re-exploit all the time in order to keep access to a system. So we shall see whether that'll work. But if we manage to move everything to that point, then we can start worrying about or fixing all the security bugs that occur all the time and try to make things harder on that front. So the hope is really implement this, and we can move from mass compromise that scales arbitrarily to tailor-made compromise that is quite costly. Important question, who's going to pay for this? None of the steps that are proposed are free. But if you really look at them, they're not all that costly either. Like, we're literally talking about a size of an investment that is probably, yeah, a couple dozen, well, perhaps even not even a couple dozen, perhaps a dozen million spread out over most of our industry. These things are not expensive to build. Like, adding a few wires to do DMA on a firmware isn't expensive. Running a public ledger isn't expensive. All these things are eminently doable. And the amusing thing is, I would argue that distribute over the entire IT industry, it'll actually reduce cost because it'll make systems easier to administer. So there should be some way of paying for it easily. And then lastly, there's always an easy way to pay for it by the security industry. We need to convince people to stop buying snake oil. Because if you look at the revenues that are being generated with colorful boxes that provide security exactly as long as nobody looks at these boxes, I think it would be trivial to pay for everything that I've proposed by just a fraction of the revenues generated with these boxes. And it's a bit sad to realize that the screwedness of the entire infrastructure isn't due to technical hardness. It's due to broken incentive structures and political complexity. So, right. Thank you. Any questions? Jörn.
Test, test. The microphone's supposed, oh, thank you.
Thanks. So would the list of signed objects also need to be signed?
So the ledger for the signed objects is actually a sort of Merkle tree. So you can't sign anything else unless it's complete. The certificate transparency guys have pretty much solved this in that sense. So yeah, and to be fair, the list of signed object, like compromise of the list of signed object, of course, is a threat. But this is at least detectable for the person that does this, right? So let's say Microsoft keeps a list of all the executables they've signed with dates and SVN tags. It should be comparatively difficult for somebody to insert something in there without Microsoft knowing. And at least if you have a vendor and somebody manages to compromise this list, at least the vendor knows roughly when this was modified then, because they know when their actual builds were. And lastly, there's liability. You know, it might just be your responsibility as somebody who provides software for others and gets paid for it to actually check whether your list is in accordance with what you know.
Thanks.
Any more questions? Please raise your hand. Okay, that looks very busy. In this case, thank you very much, Halvar, for this amazing talk.